Okay. Great.
Okay.
So I have prepared this and maybe under the form of a journal club more than like a talk presentation. So yeah, man, you will see. So I'm going to talk about using pairwise model and spin models for uncovering pattern of binary data. And in particular, I will talk very slightly about the search of why we are interested in simple spin models. And so I have decomposed this in 3 parts. The same way is because it's a journal club. The first 2 parts are a bit more of introductory parts. They are not really new things there, but they are ideas. The last part is about complexity of spin model. And finally, I have other works on minimally complex model, which is the end of the story, but I don't have really, I think I will not have the time to talk about it. So it's there if you have questions. And yeah, okay. So I'm going to start by explaining you how we model binary data with spin models. And in particular, with pairwise spin model first, and then with spin model in general. So what is the problem of, if this is too easy, you can tell me and I can go faster. So what is the problem of modeling data? So in general, in physics, we have this, we tend to, in theoretical physics, we tend to start from models and then derive properties of the system, states and observables of the system. And in case of data, of modeling data, we do the opposite. So we start from the data set, so we have states of the system, we can compute observable, properties of systems, and we want to come up with a good model for that system. So what is a good model is that we want to find a model that best capture the patterns that are hidden inside the data, even though the data is also noisy. In my case, I focus on binary data. So what is a binary data? So it's a data with zeros and ones or minus ones and ones. So data with a set of random variables that can take 2 values only. And let's say that you have several observations of the state of these variables. And so example of these are, for example, voting data, where your variables will be voters. And in each state, you're observing if your voters are voting yes or no, for example. But you could also have stock market data, behavioral data, medical diagnosis data. I mean, there are many possibilities, neuronal data also. So I can explain you, for example, in the case of neuronal data, your variables will be neurons. And then when you record your neuron, you're recording the voltage of your neurons in time. And if you want to convert this into a binary data, you have to bin your time. So for example, typically we'll take a 10 millisecond time bin. And if the voltage comes above a certain threshold, you will say that your neuron is spiking, and then you will put a 1. And if it's under that threshold, you will say your neuron is non-spiking, and you put a 0. Okay, so that's a time series. And so in many cases, those data sets are time dependent. But what we consider here is the problem of the stationary data sets. So I will really focus on stationary data. So there is always many layers of complexity. So for example, how do we do this? I will take the example of the US Supreme Court. This is a data set that comes from that paper here, Statistical Mechanics of the US Supreme Court. So the US Supreme Court is one of the it's the biggest court in the United States, is where they vote all the hardest cases. And so they have 9 justices there, and they stay for a very long time. So we have many instances of voted of these justices. So here we have 895 votes. And for every cases, the justices vote yes or no, but then they reorganize their data sets in order to have, for every cases, they knew if a yes was more liberal oriented or conservative oriented. And so they transform their data sets in under this form. So you have your 9 justices here. And for every cases, you know if the justices voted more, if the vote is more conservative, or if the vote of the justices is more liberal. And then you have many votes, you have 895 votes. And so you can then say that we will consider that those justices are random variables, binary random variables, and that can take value plus or minus 1. So they are called spins. And so the most common model that is used for this type of data is pairwise spin model or Ising model. So to model this with an Ising model, you have to assume that your system is stationary, which we talked about earlier. And then you have to assume that all the votes are independently sampled from an underlying probability distribution. And this underlying probability distribution has the form of this Ising model type thing. So you can recognize here in your Hamiltonian, the Hamiltonian of an Ising model, you have the sum of this HI-SI. So I've represented here graphically. So before putting the Ising model, I had empty variables. And now I represented the field here with black dots, right? So there is a field on each of the justices. And so this term models an external drive of the justice to vote conservative if HI is positive, or to vote liberal if HI is negative. And then there is a second term, which is a sum over all the pair of judges, I and J, of Jij times Si, Sj. So Jij here is a coupling parameter, and is represented with a blue link here. And it models the tendency of justices I and J to vote similarly if Jij is positive, or to vote oppositely if Jij is negative. So all the HI and those Jij are parameters. They can take any real values. And so what you can see here is that this P of S, so this S vector is the vector of all those variables. And P of S here, given G, is actually not just one probability distribution, but you have one probability distribution for each value of G. So this is the parametric family of probability distribution. And another thing that I want to note is that contrary to the usual Ising model, we don't know who is actually connecting to who here. We don't know who is a neighbor of who. And so we have to put any, a priori, we have to put all possible connection, because we have no notion of locality in that system. So a priori here, we have all possible Gi's. Okay, so when we take this form of the probability distribution, the next thing that we have to do is that we have to find the value of the parameters that are such that this probability distribution is as close as possible to the empirical probability distribution, so the one in the data. And how we do this, we do what we call inferring the parameters, and we find basically the parameters J star that maximize the probability to reproduce the entire data set. So what I call S hat is all the state of the system in the data set. And so if you compute this theoretically, you will see that at the maximum, so at the maximum of this function, you will see that the empirical value of the SI in the model are exactly equal to the empirical value of the SI in the data. And the same for the SI times Sj. So the average value of SI times Sj in the model are exactly equal to the average value of the SI times Sj in the data. So what it means physically, it means that this is the local magnetization. So when we fit this model, we ensure that the local magnetization in the model is exactly equal to the local magnetization in the data. And we ensure that the local correlation in the model are exactly equal to the local correlation in the data. So what we do when we take this type of parametric model, we assume that the relevant observable of the system are the local magnetization and the local correlation. Okay, and then, okay, so we can fit our parameters, we can fit our HI and Jij. And so this is what they did in this paper. They started with their observable in the data. So these are the local magnetization and local correlation in the data. From these ones, I'm sorry, the matrix is weird here, but normally it's a real like box. Okay, I don't know why it's blur, but you can still see the tendency. So and from those empirical values, they can fit their parameters. So they will fit the HI and the Gi's, such that the model distribution is as close as possible to the data distribution. And what you can see here is that the HI tend to be positive for conservative justices. So the conservative one are on this side and the most liberal one on this side. And so you can see the HI tend to be negative for the most liberal justices. And the same, you will see that the Jij tend to be positive within between justices of the same party, of the same orientation. And so this is between the conservative, this is between the liberal, and it tends to be blue. You can see the color still, between justices of different orientation. Okay, so but when you have fitted this model, then you can ask if this model capture well other pattern of the system, in particular higher order pattern of the system. You can also try to make some prediction and see if those predictions are properly verified. So it's kind of the same thing. So for example, here, what they did in this paper is that they computed the probability that you have k conservative votes in the data set. So k conservative votes means that you have a state with k plus 1 inside this state. Okay, so you can have a state with 0 plus 1, you can have a state with 1 plus 1, and to a state with 9 plus 1. And you can compute the empirical probability that you have k conservative votes, and that will give you this green line here. And you can also compute it. You can also compute this probability if you were to assume that the justices are voting independently from each other. So independently means if I go back earlier, I remove that term. I remove all the pairwise connection. I just keep the initial, the HISI term. And so if I were to assume that the justices are voting independently from each other, then I can also compute I can fit the model and I can compute the probability of k conservative vote, and they obtain these blue lines here. So what you can see is that this is not matching at all with the data one, but now they can compute this same probability of k conservative votes, assuming this pairwise connection, and they found that this red line, which is matching pretty nicely with the green line. Okay, so by doing this, they are looking at some higher order patterns, and they're checking if their models with only pairwise interaction is reproducing some type of higher order pattern of the system. And this is pretty good, so they're quite happy. But there are several questions we could ask. We could ask, do we actually need all the pairwise correlation to reproduce the pattern, all the correlation pattern of the system? Do we actually need all the pairwise interaction, to reproduce all the correlation pattern of the system? Maybe I can use only a subset of this interaction and still be good at reproducing the same patterns. And if I was able to do that, if I were able to find a very small set of interactions that allow me to reproduce these patterns, then maybe I would be happy, and maybe I would be able to say something about the structure of the system. Okay, the second question I can ask is, are the local magnetization and the local correlation sufficient to capture all the relevant patterns of the data? So what I'm asking here is, are they relevant higher order pattern in that data set? So for example, here, I could imagine having a model with a 3-body interaction, or with a 4-body interactions, or whatsoever, any order of interaction. And so this can be generalized in terms of spin models. And it's quite easy. You can add term in your Hamiltonian here, which will have this form. So that would be a JIJK. So J457 for that interaction, for example, times S4, S5, S7. So that would be your parameter, and that would be your spin operator. And here I can add also a 4-body interaction, which would be this one. And I would take the form of J1289 and S2, S8, S1, S2, S8, So what do they mean, these high order interactions? So if you were to interpret them, if you were to try to interpret a high order interaction in the system, it's actually quite complicated. A high order interaction model a tendency of the justices, for example, a 3-body here, model a tendency for justices I, J, and K to vote according to this type of pattern. So let's say 1, 1, 1, or -1, -1, 1. So let's say you must have an even number of liberal votes in the system. So if JIJK is positive, this means that this represents the tendency of justices to vote according to this weird type of patterns where you have an even number of liberal votes. And if JIJ is negative, then this model the tendency to vote according to this type of patterns. So that sounds a little bit crazy, and it's even more and more crazy when you add higher and higher order patterns. But for example, I analyze some type of behavioral data between songbirds. So I had the data of the songs of all the birds during a course of a season. So, and from those data, you can binarize the data, and then you can come up with, in each bean, is a bird singing or not? And then you can try to look for irrelevant pattern of this type of data sets. And interestingly, in this type of data, you have relevant three-body interaction. And what do they represent? They represent some type of love triangle. So basically, when the male is singing, a male that is mating with two females, whenever this male is singing, only one female is replying and the other female is always silent, and reciprocally. So this will look like something like that. So one male is singing, a female is singing, but the other one is always silent. And so this type of pattern are very relevant in this type of data set. And these are relevant three-body interactions.
Just one question. Did people find these interactions in the model you showed before of the US court, like higher order?
So in the US Supreme Court, so I will not talk about it here, but the most relevant pattern there are pairwise actually patterns.
So they didn't find any.
So yeah, so it's not that easy to say. So it's a very long story to say. Okay. So the most relevant pattern, the really most relevant one, so that you can organize your pattern in terms of how relevant they are. The most relevant one are pairwise. Then you have some. You have to add some higher order pattern if you want to model properly the data. You can add some higher order pattern if you want to model properly the data. Yeah, so this I will not talk about it. It's actually in the other pattern minimally complex model. Okay. But maybe we can come to it at the end again. So in the US Supreme Court is mainly pairwise, which I think is also interesting. Okay, so more generally, you can write down the most general form of spin models like this. So you can choose your skeleton, which is a set of interactions. So here I took models with 4 random variables. There are 4 spins, and I gave you 3 examples. And I will call M the skeleton. And so your Hamiltonian now is a sum of the interaction belonging to this skeleton, to this model M, of a certain parameter that I call J mu times a spin operator that I call phi mu. Okay. And so why this is, so we saw that it's difficult to interpret higher order interaction, but in fact, this is more rigorous because all the phi mu, if you take all of them, there is 2 to the n minus 1 of them, they form a basis of the space of function from -1, to the n to R. So they map the entire space of function for binary data. You can model any type of patterns of binary data with this type of function. So this is rigorous. Okay, so, but now how do we select among those models? So you see there is 2 to the n possible type of interaction. And with 2 to the n possible type of interaction, you can compute 2 to the 2 to the n possible model. So it's a super exponential family of model. And so it's a complicated thing to do a model selection procedure. And so this is the second part. I will explain you what is model selection, why it is, I think, important to do model selection, in which context it is important, and what does it mean to perform model selection. Okay, we saw earlier that when we choose a form of the probability distribution, we make a selection already. We select what we consider are relevant observable in the system. And so what does this mean? It means that when I fit my model, I basically assume that I will put all my observable, the observable are the average value of the operators, of the spin operators. So if I put all the model observable on the x-axis and all the data observable on the y-axis, then at best fit, I will put the selected observable, the relevant one, on this x equal to y-axis, or very close. Okay, and then the other observable will be somewhere around that axis, maybe somewhere anywhere in that graph. And if I assume my system to be stationary and my model is good to capture the statistics, all the pattern of the system, then it means that somehow all the other observable will end up in some type of standard deviation from that x equal to y axis. So this is assuming the system stationary. This standard deviation is proportional to 1 over square root of n, where n is the number of data points in the system. So for example, if I do it with the US Supreme Court, then you can see that this is in the case of a pairwise, a fully connected pairwise model. I will have the pairwise interactions, the pairwise observables, and the field observable will end up exactly on that x equal to y line. And all the observable will be somewhere in that graph, and they end up to be very close to within 1 standard to 3 standard deviation from that line. So it is pretty good at capturing all the higher order pattern of the system. However, this model has 45 interactions. And I could play around and find another model with 45 interactions. So you see, it's actually a bit different. It's not the same model. The dots are not placed in the same way. And this model has also 45 interactions, but they include higher order interaction. I selected some other interaction. And these perform also pretty well. So the fact that we're able to fit well doesn't necessarily mean that we found something interesting about the structure of the system. It just means that we found a model that is capable of reproducing statistics of the data. But it will not tell us something, what is really important about the system. Okay, so, but you can also show for this US Supreme Court data, you can also find a 15 interaction model that also capture quite well the data. So this one has only 15 interactions. And so if you're capable of doing this, then you will start to think that maybe those 15 interactions capture something more interesting than the 51 interaction I had earlier. So, so where I want to go here is that by choosing the form, to summarize here, is that by choosing the form of the model, we make an assumption of what is relevant and what is not relevant in the system. And deciding what is relevant is not easy because we actually don't know from the start what is relevant. And what we can see is that we can select many types of models that would fit almost equally. So what if we really want to understand something about the structure of the system, we need to select the model appropriately. And that's not an easy thing to do. So how do we do this model selection procedure? So to give you an intuition about it, I took an analogy with polynomial function. So assume that you have an XY, you're measuring some data, let's say, I don't know, a pendulum, you're measuring the position of the pendulum in time, for example. I mean, this is not exactly that, but that will give you on Y the angle and on X the time, the position, sorry, on X the time. And so you can have, so you have an XY graph here, and you have your dots, and you want to fit that with a polynomial. And you could ask, do I want to fit this with a linear function? Do I want to fit this with a second order polynomial? Or do I want to fit this with a 15 order polynomial? So because as a physicist, you will obviously say, okay, this seems to be not really good enough. This is way too much. I fit all the noise and I'm not interested in the noise. So if I really want to understand something in the system, I'm going to take maybe something intermediate like this second order polynomial, which means what I'm doing intuitively is that I'm doing this balance between model complexity and fitting. I want a model that is not too simple because otherwise you will not be able to fit well the data. But I also want the model to be not too complex, to be able to capture only the main pattern and not all the noise with it. Okay, so with spin model, we want to do the same thing, but we have a higher order system. We have a higher dimensional system. So how we do this? There is several ways of doing this. There is the two most common ways are to use Bayesian model selection or to use minimum description length principle. So what is the idea in Bayesian model selection? What you will do is that you will try to find the model that maximizes the probability to reproduce your entire data set. And this model, by model, I mean here the skeleton. So you have to integrate over all the value of the parameter given a certain prior on your parameter. Okay, so that's not so easy to compute because you have to compute this integral. And the second approach is you will try to minimize the number of bits that is needed to represent your data set. So initially your data set has, for example, it's a binary data with, let's say, small n random variable and large n data points. So you have small n times large n log 2 bits to represent your data set. Now, if you use a model, by using a model, you'll be able to compress this representation, you'll be able to compress these data sets. And the compression is given by this formula. And so the first term in this formula is basically minus the maximum log likelihood. And this tells you how good are you fitting your data sets? How good is your fit? So, and the second term is represent how complex is your model. So what you have to do here is to compute how many bits you need given a certain model to represent your data. You have to first write how many bits you need to represent your model, which is this model complexity. And then given your model, how many bits do you need to represent your data? How far is your data from that model? So how many extra bits you need to explain how is your data set? Okay. And so you want to minimize this because the idea is that the model that minimizes this, that is able to compress the most, that is able to minimize this function, is the model that will capture most pattern from your data set. Okay, if you have questions, you can ask. So in general, all those quantities are pretty hard to compute. So it's hard to compute this one because you have your integral. This one is not hard to compute, but you have to do a gradient descent, so it's computationally demanding. This one is generally hard to compute, and we will see what it is in terms of spin model. And on top of it, you have a super exponential family of spin model. So this problem is in general pretty hard. And so that's the main reason why I think most people use, that's one of the reasons why most people use pairwise model. So there are several reasons. We saw earlier that pairwise interactions are easier to interpret. This seems to be also quite good to feed data, but also the problem is simpler. There is less number of model. You have only 2 to the n square. There are good algorithms to perform model selection. You have plenty of algorithms now to perform model selection among pairwise model. But the question I want to ask is this justified? Because we already perform a model selection. We already assume what is relevant or not in the system. And in particular, I want to know if pairwise models are actually simpler. Do they have a simpler complexity here? And so this is the work I'm going to talk about here, which is spin model complexity. And in particular, we'll ask the question, are pairwise model really simple? And by the way, you can tell me if I'm going too slowly because I try to explain step by step, but maybe this is too easy. So yeah. So, okay, so we want to know the complexity of a spin model. So I'm going to ask you, here I've represented 3 models. The 3 of them have our models for 4 spins. So there is 1, 2, 3, 4 spins. And 3 of them have 7 parameters. And there are some fields. There are some variables that are left without anything. There are some fields on some variables. There are some pairwise interaction. The triangle here has 3-body interaction, and the blue triangle are 4-body interactions. So between those models, I would like to ask you what you think, which one is the simplest? Intuitively, I don't know. So maybe I can ask, I don't know, maybe I can ask who would think that this one is the simplest? You can raise your hands. I don't know. Okay, so there is 1 person. Okay, so who would think 2 person? Who would think that this one is the simplest? Nobody. Okay, and who would think that this one is the simplest? Okay, I have 4 or 5 person. Okay, so right now we decide that this one, we think that this one probably is the simplest. There are 5 people who think this one is simplest. So let's see. So how can we compute the complexity, and in particular, is this one actually simpler? So what is model complexity? So there is actually an expression for model complexity. It comes from this paper by Risanen, Feature Information and Stochastic Complexity. And you can write down the model complexity there are several terms. So the first term here is proportional to the number of parameters in the model. So earlier we saw we have only model with 7 parameters. So this term is identical for all those 3 models we just saw. And this term is proportional to log n. So n is the number of data points in the system. Okay, so this is proportional to log n. Then the next term is of the order of 1. And this term is called geometrical complexity. How complex is the model given how you have chosen your interaction, how you have placed your interaction. And so because this one is of the order of 1, in general, you will compare this term for models of the same number of interactions. And then the next terms are of the order of 1/n. So we are looking at things that are smaller and smaller, but this becomes relevant when you have finite data sets or small data sets.
So can I ask a question?
Yes.
How do you come up with a formula like that?
Okay, so this formula was computed in this paper, so I didn't invent it, but you can compute it by okay, so there are 2 ways you can compute it. So the first way is but both ways is using an expansion. So the first way I will is basically earlier I show you that these 2 approaches here. You can show that if you take an expansion for large n of this approach, of this integral, you will recover that formula here. So if you make an expansion of this integral for large n, you will basically find these 2 terms, or you can even compute more terms. This term comes from the how to say. When you're doing your saddle pod approximation, when you're doing your expansion, you have to this term comes from the integral of the how to say it comes from the integral of the prior at best fit. So here I had to make an assumption. If you want to recover this, you have to make the assumption that the prior that you use is Jeffreys prior. And yeah, so that's one way. It's not the way Risanen used here. He also used an expansion, but he used some information theoretic approach. I will not be able to explain it like this, I think. But yeah, you can find it in this paper, and the expansion is similar. Yeah, so basically the simplest way is to take this integral and expand it for close to the maximum. So to make an ascendant product approximation, close to J star. Okay, so and so this CM then will take this form. And so if you make this expansion, you have to assume Jeffreys prior to recover this form. So what do you have here is that this I here is called the Fisher information matrix. It's for spin model, it takes this form, is the Hessian of the log of the Partition function. If I were to make us okay, so the idea is that the more complex is the model. So a model that is more complex is a model that is more flexible, which means that it can fit a broader type of data sets. Reciprocally, a model that is very simple is a model that is capable of fitting very few type of data. And in general, this quantity is difficult to compute, this integral. And if I were to do a small information geometry break, when you have your parametric family so when you decide for a model, so a skeleton, you have a parametric family of probability distribution. And so this defines a k-dimensional Riemannian manifold. K is the number of parameters of your model. And in this manifold, each point is a probability distribution. Okay, so on your axis here, you have the parameter, this is parameter space. And the natural metric on this for this manifold is given by the Fisher information matrix. And so interestingly is you can write down your Fisher information matrix under this form, which is a covariance matrix or susceptibility matrix. And what you can see here is that this matrix tells you how susceptible is the statistics, how susceptible is locally the statistics of your models under variation of your parameters. So if you change a little bit your parameters, how broad your statistics will change. And so the complexity here, this integral here, is the integral of the volume of the entire manifold. So this is this local volume in the manifold. Okay, so this was just a small parenthesis. And so now, now that I gave you the formula, if I were to ask you which model is the simplest, using that formula, I mean, it's still not easy, right? So, so let's do a small thought experiment, and maybe that would be easier later to answer that question. So I'm going to take a data set and I will give that data set to Bob. And Bob has this magic model selection procedure, and he's capable of selecting among all possible models. So he ranks all possible models, assume that he makes, for example, he has a way of computing the posterior probability, and he computes the probability, this probability for all possible models. And this is a data set on 3 variables. And he finds that the best model is this one that has 3 fields and 1 pairwise interaction. Now he gives his data set, he wants to be sure about what he's doing. He gives his data set to Alice, and Alice she sees the data set in another basis. It's the same data set. There is no nonlinear transformation. It's just a bijection of the variables from the variables Si to the variable sigma I, and there is no added noise. Okay, so Alice run the magic, this same magic model selection procedure. She can compute the posterior for all possible model, and she will find the model. Can you tell me what you think would be the model here? Or, yeah. So do you have, any of you have an idea of how the model might look like here? Okay, so a priori, we can think that the model that is here will be a transformation of that model under that transformation here, right? So if the procedure is perfect. And if I were to do that transformation, I have to take all my interaction one by one and transform them according to that transformation T. So if, for example, if I take the field that is on S2 here, so field on S2 is associated with the operator S2 alone. And the operator S2 is equal exactly to sigma 2. So field on S2 will be transformed on to a field on S2 for the new model. Now, a field on S3, the same will be transformed to a field on sigma 3. Now, if I were to take the pairwise interaction between S1 and S2, this is associated with the spin operator S1 times S2. If I want to recover S1 times S2 with now the sigmas variable, I have to make the product of the 3 of them. Because the product of the 3 of them will give me S1 times, I have to make the product of sigma 1 times sigma 3. If I take the product of sigma 1 times sigma 3, I will have S1 times S2 times S3 square, and S3 square is always equal to 1. So any spin variable squared is always equal to 1. So then I get now a pairwise interaction between sigma 1 and sigma 3. And the same, if I take my spin variable, if I take the field on S1, then this field on S1, to recover that, I have to make the product of all 3 of them. Then I will have S1 times S2 square times S3 square, that will give me S1. Okay, so that will be a 3-body interaction. So what you can see is that this model is just a transformation of that model under this ejection. Okay, so what we know here is that these 2 models must be as complex. And we also realize that it's difficult to guess from the look of the model which one is the most complex. Because here we have 3-body interaction, and in particular, the pairwise model are not necessarily simpler, and the complexity of a model is not related, it's not dependent of the interaction, of the order of the interactions. And so we can define those transformations, we call them gauge transformation. What we know is that they preserve the number of interaction of the model, they preserve the number of degree of freedom of the model, and they preserve the intrinsic architecture of the model. So the constraint, the loop structure of the model. For people who are familiar with this, the loop structure, this entire thing can be recovered by making an expansion of the partition function in terms of loops. So there's this loop expansion, this whatever. So you can make this expansion and recover exactly the same results.
Just one question. How did you see immediately like that one has the same complexity as the other?
Sorry, can you explain?
How did you see immediately that one model has the same complexity as the other? I know you did the transformation, but how do you?
Okay, so it's a bit of an indirect reasoning. The idea is that if the model selection here is perfect, then so there are 2 things. So the first one is if the model selection is perfect, then the model that you will find is the best compression of the data set. Now, if you look at the data in another basis, it doesn't matter in which basis, it doesn't matter in which basis you're looking, the type of pattern that you have in your data will not change. So they will be represented in another basis, but the main pattern should be the same. Okay, so the compression, so if you do this perfect compression, use this perfect model selection, then you should find the same compression, so the same model. Another way to see this is basically this model is just a transformation of that model under a bijection. So you're basically looking at the same model, but projecting in a different basis. So it is exactly, because it is exactly the same model, it has the same complexity.
Okay.
So if I were to do a small break for a bit of a more mathematical break, so all the spin operator, the set of spin operators is a group, is Z2 to the n, and is a group generated by those n variables. And what we call gauge transformation are the automorphism of that group. And so this transformation, they preserve the partition function. So all the models, all these gauge transform model, they have the same partition function up to permutation of their parameters. And they have exactly, because they have the same partition function, and they will have exactly the same Fisher information matrix, because the Fisher information is the Asian of the log partition function. Okay, so the model sorry, it's not the same model, but the gauge transform models, they have the same Fisher information matrix, and so they are associated with the same statistical manifold. And so basically they are the same model seen in different bases. And we can start from one model and we can map many, many models like this, and we can compute. So if you take all possible model, all the 2 to the n model, you can now divide your space of model in classes of equivalent model. And so this is for an example of a class. So here you had this model that we saw earlier, and you can see that this model, you can make gauge transformation to map this model into this model or this other model. And they are this is a class of models with 4 spins, 7 interaction, and 15 loops. All these models have 15 loops. The loop are some constraint between the operators. They are basically product of spin operators that are equal to 1. But okay, I can enter more in detail in this if you want later.
Okay, can I ask a question?
Yes.
So you mentioned that there in total there were sort of a super exponential number of models possible, but if you consider all these gauge transformations, how does that change? Like how large is the equivalence class of models?
So that's an interesting question. So I computed. I mean, so you can compute numerically the number of classes for a given number of. You can compute the total number of classes for a given number of spin operators, a number of spins, and this seems to increase almost also super exponentially. So it increases less fast, but and I don't have a general formula, so you can use basically Pairwise theorem to compute this number of classes, and I can compute the number of classes for, let's say, 4 spins, 5 spins, 15 spins, 16 spins, and that's it. I don't know how to compute later. I don't know. Yeah. So, but maybe for some of you this will be familiar because so I looked at this with other people who are I basically look at this with 2 other postdocs. And they came up with the Pairwise theorem because I'm not capable of doing that. It seemed that this is very similar to linear code. So this is one of the questions I would like to understand better, how this map with linear code. But yeah, so that's a question I ask maybe later. Yeah. Okay, so if I were to compute the number of classes, for n equal to 4, so this is an example. If I have a system with 4 spins, then I have only 46 classes. I have 32,000 models, but only 46 classes. So it's still a drastic reduction. Each triangle here is a class. So behind each triangle, there is many models. For some of them, I gave you a representative model. The colors are the number of degree of freedom of the model. So number of degree of freedom is number of independent operators in that model. So for example, if I take this model here, this class here with 1 representative like this representative has 3 fields and 1 variable is left free. So whenever you can have a model of the class that have 1 variable left free, then it means that the number of degree of freedom is not 4, but is smaller. And in that case, it will only be 3. Okay. Okay, so and so you can go up to 4 degrees of freedom. And you can see that the more degree of freedom, the more complex is the model. So if you fix a number of parameters, here is a number of parameters k. If I fix a number of parameters, the more degree of freedom, the more complex. The other thing you can see is that there are 2 limit lines. One limit line is a line of the independent model, sorry, this one, which is basically the line where you will find the models that have only fields, for example. So this has 3 fields, this has 4 fields, this one will have 2 fields, and this one field, and this one will have nothing. Okay, and then this line is the line of the most complex model. And then here you have a line of this bottom line is the line of subcomplete model. So all model on this line, there is at least one representative that looks like that, which is take a subset of the spin, so here 3, and put all the interaction on that subset. So we call it subcomplete. So for example, this is subcomplete on 2 spins, this is subcomplete on 3 spins, and this one is subcomplete on 4 spins, which is completely complete model. Okay, so what you can see here is that the idea is that the most compact is the model, the more constrained. So more compact is the model, the more constrained it will be, and the simplest it will be. So a more compact model is capable of fitting less type of data. Oppositely, a model that is more spread out, like a fully connected pairwise model, tend to be more complex. So we tend to involve less constraint, and it tend to be more complex. And so as a consequence, it tend to fit broader type of data. Okay. So so as a conclusion here, we saw that complexity does not depend on the order of the interactions, and it's not an easy thing. You cannot see directly from the visual representation how complex is the model. That there are equivalent classes of spin models. So there are models with pairwise and models with higher order interaction that belong to the same class and they have the same complexity. That the simpler models, they are the ones that implement more constraints. So they have less degree of freedom, they are as compact as possible. And in particular, pairwise models tend to be more complex. Fully connected pairwise models tend to be more complex. And so more complex models have more constraints, and so they account for less variety of data type. And so they are easier to specify because they can model only very few type of data. So if you're able to model your system with a simple model, then you'll be very happy because you will know that that model will only be able to model what you have and nothing else. So that's the idea. Okay, so now if I come back to the same picture we had earlier, and I ask you which is the simplest model. So I don't know if this is something that, oops, sorry. I lost the presentation. Okay, so if I come back to what we have earlier, then we can see that those two belong to the same class. So they have the same complexity. And this one is actually more complex than this one, is what is represented here. So this one is actually the most complex, and those two are the same complexity, and they are the least complex. Okay, and so the interesting conclusion we can draw here also is that pairwise model selection is actually basis dependent. So if I were to restrain myself only to pairwise model, and I give my dataset to Bob, and he finds the same pairwise model, so he's very happy. But now he gives his dataset to Alice, and Alice is only capable to model using pairwise model. And then she will be quite annoyed because the model that she will find will not be a transformation of Bob's models. So pairwise model selection is heavily basis dependent, right? So that's another conclusion I wanted to draw here. And so if I were to go back to our initial problem, now we have this very hard problem, and we know we cannot use pairwise model. And so one of the issue here is because there are many models. One of the issue is that we don't have a notion of locality. So if we were to have a notion of locality in that system, so by locality, I mean if we were to have an idea of who is more likely to be connected to who, then we will be able to reduce drastically that data, that set of models. And so the procedure that we proposed for that is to use what we call minimally complex model for doing the model selection. So the idea, and I'm not going to talk about it, but the idea of that model selection is that we will try to find, we will try to map the data, to project the data onto models that tend to have this type of structure, which is subcomplete on a subset of spins. So they are minimal complex models are composed of independent subcomplete models. And so by doing this, we were trying to find communities in the data set. What are the variables that tend to be very dependent on each other? And what are the variables that tend to be very independent from each other? So we will try to find a notion of locality. And what is interesting with this type of model selection is that we don't have this problem. So using minimally complex model, the model selection is basis independent. And the second thing is that minimally complex models tend to be simple models. So this is another reason why it's good. And then the last thing that is nice for this type of model is that these quantities are easy to compute. So yeah, so that's one of the interesting things we can do. And then there are many random sorts, but I'm not going to enter into those random sorts. I don't know what happened here. Yeah, so then there are many random sorts, but yeah, I don't want to enter into it. So this is the people I worked with on spin models in this box, and mainly Matteo Massili and also Paolo Mazda for the minimally complex model. And then the counting equivalent classes that we talk about, I looked at it with Danilo and Matthew de Cross. And then we try to do application on data, so on real data. And so these are the people. Yeah, so if you have questions, I took a lot of time, so yeah. If you have questions, yeah, don't hesitate to ask.
Does anyone have any questions?
I can ask a question.
Go ahead.
Thanks a lot for your talk. It was very nice. So this set of gauge transformation that you find on this on these spin models, is there some way in which they form a group, like a mathematical group?
Yeah. So they are the automorphism of that 2 to the n, so they are a group. And so you can count them. They are. It's easy to count. And you can. So the interesting thing, I think I put it here. You can write down. You can write down a model as being a linear application between the space of operator and the space of variables. And so the gauge transformation are the automorphism of your arrival space. And so the degrees of freedom of your model will be the rank of that linear application, and the loop structure will be the kernel. And so you can use this is what I used basically for doing the data analysis. You can use this linear. This is a linear application can be represented as matrices, binary matrices. And so this is the only way I do all the data analysis is by using this binary matrices representation. So the gauge transformation now are just binary matrices of size n by n, and they are invertible. So you can sample if you want. You can do, there are funny things that can be done. You can map, you can fit, you can start from a model and make a Monte Carlo simulation where you sample randomly gauge transformation and fit your data with many models from that class and try to see if the one model of the class fits better the data. And yeah, there are many things you can do using the matrix representation. There are many things you can do. And I think this matrix representation is somehow connected to linear codes, but I'm not familiar enough with linear codes, so I don't know. But when I was trying to count them, I was doing this type of graph, which I didn't know are also used in coding theory, I think. And so using this type of graph, you can count them by hand for n equal to 4, n equal to 3, n equal to 4, and you can start counting for n equal to 5. But it seems that this is similar also to linear code. So if one of you
Okay, so you don't, so at this moment you don't know if the number of equivalence classes of models grows exponentially or linearly or polynomially with system science?
So it grows the fastest than exponentially. So you can, as I was telling you, you can use Pouliot's theorem to count how many classes you have for and up to n equal to 15, I would say. And this grows faster than exponentially. I don't know if it's like super exponential, but it's faster than exponentially for sure. Yeah. And then there are other interesting thoughts. I think so. This you know, this representation I showed you earlier with all the observables is actually a Fourier space representation. So basically, all the observables are the Fourier transform of the data set. And what you can do is in this space you can do. I mean, I would like to understand better how this space looks like and what type of pattern we can extract from this space. But in particular, you can play around and isolate variables in that space. So, for example, if I take in black in the back, there is all the observable. If I take all my variables, now in red is all the observable if I remove one of them. And so here I remove, it's the same data set, but here I remove, let's say, the first one, here I remove the second one, here I remove the third one. And so it is interesting because I think this is somehow connected to this partial information decomposition thing. I think, Rink, maybe you're more familiar with this, but yeah, so I think that could be useful in that context. But yeah, so these are random thoughts. I'm trying to connect with people of the community. Yeah. Sorry. Yeah.
So would you be able to play this kind of game also in, you know, for systems in which it's not most likely going to be a spin model? So for other types of, yeah.
Yeah, so that's also something that I would like to do. So I've expanded, so you can do the same for discrete data. You can, for discrete data, the usual thing is the POTS model. And you can generalize the POTS model to include high order interaction. And you can also compute, you can do the same, this pattern function expansion. You will still have the loops and you can have occurrence classes as well. So but it's so complicated. I mean, to me, it's too complicated that I don't manage to use this yet for analyzing data with it. So, but you have the same thing. So you have equivalence classes, you have, right. And then I would really like to understand how this works for continuous data as well. This is definitively something interesting, I think.
I have a more sort of exploratory question, also because I feel it connects a little bit with some things that Surush was talking about at some point about, you know, how do you find the best model to fit stuff. I was just wondering, Surush, if you had something to say about this.
So the way that I was looking at this was slightly different. It was about, given a set of probabilistic information, what would be the least informative model? So the best model in that sense was the model that was least committed. So it assumes the information that you have, and beyond that, it remains as unequivocal as possible, essentially. So it's a slightly different type of best model here.
Right.
That we are dealing
I see.
I think the notion of goodness there was about being non-committal.
Being not what, sir?
Non-committal. So essentially, you assume the information that is forced by you, by the evidence, and beyond that, you remain as essentially open as possible. So that was the notion of best model that we were dealing with there.
Does anyone have any other questions?
thanks. Sorry. I hope I did not make it too complicated.
No, it was good. Yeah, I thought it was right level. Okay, so I guess if no one has any other question for Clélia, then let's thank Clélia again for the presentation. Thanks a lot. Thanks a lot.
Thanks, Leah.
Thanks.
Jay, do we have any information about the speakers for early May? So I told you what Ule said. He said that he
Yeah.
won't be able to do it because he's very busy.
Ah,
You didn't
yeah.
get any response from Vincent?
Yeah, damn. Yeah,
Yeah.
little douche. Yeah, but I guess that's how it is. So, I mean,
Ule said he would be very interested to do this, but he said that he needs to put together a talk from scratch.
yes.
And that would be not possible for him to do it in the next week. So a couple
Yeah.
of months later, he might be interested to do that.
Yeah. Okay. Well, if you can book him for later, that would be nice. I mean, there is a gap in the schedule at the moment, which is the 15th of April.
Mhm.
So there's no one there, and then, you know, basically after the 6th of May is pretty much open.
Yeah.
Yeah.
So two other people I mentioned I've written to, I'm waiting to answer to get to hear from them. And also Sonia and Alexandru can also give a talk. So they're teaching heavily this block, but after that,
I
they
see.
will be more free. So I talked to them as well, and they said that they would be happy to give a talk as well.
Okay. Yeah. It's hard to get these philosophers, epistemologists into giving a talk, huh? They're all very busy. Yeah. I'll try to think about who could give the seminar on the 15th of April. I guess Mauricio, this Maximiliano never replied to you.
No, maybe I could try to ping him again, and I mean, it could happen that he just saw my old Yahoo mail and he thought it's spam, right? So
Okay, yeah, all right, yeah.
so maybe I should try from a more official
from a
account.
serious thing. Okay, well, I mean, if you could try and see if you could do something on the 15th of April, it could be good. Yeah.
15th of April, we need now somebody. Okay, I'll
Yeah,
try.
that's the gap. I mean, if he can't, we'll find someone, I'm sure. But yeah, that's the thing that is missing now. Yeah.
Yeah, sure. I'll ping him again and see if from a different email and see if that works better.
Yeah. All right.
And you also said that we should send you the list of publications that we have, right? With
Yeah,
the...
since you began, yeah, that would be nice.
Sure.
Yeah. I have to make a sort of database for this. Yeah.
What, the new ones or old ones?
Yeah, since you began.
Okay.
Yeah. By the way, did you get more students this time?
No, it was the same two students. I mean, I like these guys because they showed up, but they're really nice. But it's the two guys.
Oh, two people only.
No,
yeah,
no, but this is because Mauricio decided to do pre-recorded videos.
Yes.
I mean, the thing was that I needed to do the pre-recording because I wasn't sure if I was even going to have reliable internet on the day of the lecture. So I just chose to play it safe. But yeah, I think it should be better if
No,
you do
yeah,
it
the problem is that these guys, this is an honors course, right? An extra sort of course, and I think they feel that it's very difficult to have to watch lectures outside the course hours and then go to the course hours.
Right. I mean, actually, there was another girl that did connect, but then she was just for a short time. She was from physics or something, so I think she got it all. It was easy for her. But then also Simon connected yesterday, and I get the chance to chat with him. And actually, he told me that in the work groups they are working quite a bit, and they're
they all go to the work groups. Yeah, they all go to the work groups. So
it's a bit funny because in the end, I think the teaching assistants are like the most like the constant on the course, right? They in some sense,
but they are the constant on the course.
So they know the students the best, and
yeah. But I mean, if it wasn't for them, it would be an issue. Yeah. Yeah. But yeah, Yeah, because before you began, I mean, all the students were joining the classes. Yeah, yeah. So this must be the pre-recorded stuff.
Yeah, for sure. So I mean,
Yeah.
no, I don't take it.
Yeah,
I
you
don't
don't take
take
it
it hard.
personally.
No, not at all. Not at all.
Okay, nice. Yeah, cool.
Cool, guys. Well,
Yeah. All right. I guess I'll see you next week.
Yes,
so Rich, by the way, are you still in? You're still
I'm
in
still
Germany?
in Germany.
Yeah,
Yes,
okay.
you as well.
No, I managed to make it here, so I'm
Oh,
leaving
okay.
after, but I don't have an apartment, so.
But you have something temporary or what?
Yeah, I mean, yes, I'm not under a bridge, but
Yeah. Okay.
but yeah, I have something temporary at least until the 20th of April, and then I need to find either an apartment or the next temporary thing, and then.
Well, but you find it hard, or I mean, did you get help from the department?
I mean, they did send an offer, but it was really far away. So I mean, it was in
Iceberg.
Iceberg, yeah.
I mean, I like Iceberg. So
You
I
like
mean,
it?
Quite nice, actually. Yeah.
yeah, I mean, you're like 20 minutes by bike from the university, and you're like 25 minutes to the center.
On tram, right? Or by university,
On
or
bike
by
also.
Bike.
bike too?
Yeah.
Yeah.
So actually, yeah.
Do you live there, or where
No,
are you?
no. I lived in Princeton Island.
Mm.
It's a very special kind of thing. It's a small island next, 5 minutes by bike away from the train station. But
Okay.
as soon as you get in there, there's no noise. It's a
complete.
really amazing place, and it just has one street. It's kind of a square, but it also has the highest rents in the whole of Amsterdam.
I
And
see.
I'm not, and it's not that I like to pay a lot. It's just that I got a small place that was affordable.
I see.
Mm.
So you were like,
So-
I mean, the thing for me is
but
I am.
but in those places, like you can compare like an apartment there, an apartment anywhere else. It's at least €1,000 more.
Fuck.
Oh, wow, that much. I knew it
It's
was more
really
expensive.
it's really a really rich like it's only like really rich people. I mean, I don't think there's maybe one block which is kind of social housing, but the rest is.
Mm.
But it's really amazing. It's really an amazing place. So if I wasn't living there, I would probably try. I would probably try Iceberg.
Well, for me, I mean, I'm a big city boy, so I
Yeah,
like the
all right,
I like
all
the
right.
noise. I like the noise.
Yeah. Okay. All right. Yeah. All right. No. I mean, I also like the noise, but I also don't like the noise. So
yes.
I stay
Yes.
there. It's like quiet.
And
I
then
can
you
walk
have
around.
quick access to the city.
Yeah. I mean, I walk. I cross the bridge. It's less than 5 minutes. I mean, I'm in the middle of Haarlemmerbrug, so it's like.
I mean, that sounds nice.
Yeah, so it's a trade, but yeah, I get it. Yeah, so if you don't want to be like in a quiet zone, it's not Iceberg then, because that's really residential and it's mostly for families.
Yes.
Like families love that area because it's yeah, so yeah, but it's not impossible to find affordable things in the city.
No, and I think actually it's not a bad time to look now because it seems a lot of people are leaving and not. I mean, I guess more than normal.
Yeah, a lot of people left, yeah.
The net flux of people is out right now.
Yeah,
So
I think there's a lot of people leaving also because they don't need to work, physically there anymore. And there's a lot of commuters and a lot of expats.
right.
So why would they stay there with high rents?
High rents.
And,
And why would I come here?
yeah, yeah. Why did you go there? Yeah, I guess you have a visa issue, right? But otherwise.
I mean, it was because I didn't have any more an apartment nor a visa, so
Yeah, exactly. Yeah,
I had to do it.
Yeah, exactly. Yeah. But I mean, there's also affordable rent, like or more affordable rent in Diemen. This
Diemen?
area, Diemen, yeah, this area, which is sort of, it's not Iceberg, it's the opposite to Iceberg on the other side of the science park, and that is, I mean, okay, it's still not like the city, but it's less Iceberg. There's more activity. It's where a lot of people live, like who work at the science park.
Yeah, I
But
see.
it's more affordable and it's still like 20 minutes by bike from the city. So,
Yeah, but this is generally the very good thing about Amsterdam. I mean, most of the places you can get to the city center rather fast with your bike. I mean,
Yeah,
20 minutes to half an hour, you're in the city center from almost anywhere in Amsterdam.
Yeah, I was thinking today with the wind, and it's like, oh, there's this wind, and
No,
there's
the
a little
wind,
bit
the
of
wind,
rain.
yeah, the wind is screwed up. I mean, sometimes even though it's almost flat, I mean, sometimes you're like, you feel like you're climbing a mountain because of the wind.
Yeah.
Yeah. But I mean, it's not every day, huh? I mean, it's
Yeah,
not every day.
I'll have to experience
And the way back, the wind always helps, right? I mean, it's not like it's kind of constant, so it doesn't help one direction, it helps the other.
So the net effect
Yeah,
is
that
zero.
it's all right. Yeah, it's all right. Yeah. But yeah, to find affordable places in the city is more difficult. Yeah, affordable.
Well,
I mean, if you're willing to pay 1,500, you're fine, I think.
yeah, I think that's more or less what we've seen. I mean, I'm with my girlfriend,
Yeah.
so I mean, she's not working right now, but at some point
Yeah.
she will. So in that case, then it's gonna be
Yeah, but 1,500. Okay, I still think it's like a crazy amount of money, 1,500. But
It
this
is
is sort
crazy.
of it's sort of the normal thing, and 1,500. Your salary is no children, right? No children.
Right.
Then it's okay.
Then it works out. Yeah.
It works out fine. Like you still have a lot of cash to do whatever you want. But yeah, with the children it's more difficult because it's double rent. It's like it can be 1,600 if you put the kid 4 days a week in the.
Yeah, this is what I heard. It's insane, man.
Yeah, it's insane. You can get money back, but if your partner doesn't work, you don't get money back, and then you have to pay 1,600. I had to do this for several months when I went to Amsterdam.
Wow.
You have family. You have kids.
Yeah. At that time, I only had one, but yeah, we was going to the kindergarten, and I had to pay this amount of money because my wife was not working, plus the rent. So it's
I mean, that's
it's
like,
insane.
okay, here's your salary. Let me just give it to you guys.
Yeah, no, it was a bit like that. It's a bit like that.
And I get my 100 euros for my groceries.
Yeah, exactly. No, but that was it. That was it.
Brave man.
Yeah, yeah. I mean, it was supposed to be. Yeah, it was temporary, but still, for several months, I had to do that.
Are you in Amsterdam now, Jay?
No, I'm in Denmark. Yeah.
Denmark.
Yeah, because my wife is from Denmark.
Ah, okay. So you can just go and just pick Vincent.
No, yeah. I mean, yeah, I'm a bit surprised that he doesn't reply, but
Yeah. It's this.
so, but, yeah. Anyway.
Well, okay, guys. Well,
Yeah. I'll see you at some
Okay.
point.
See you
see you
next
around.
week.
Bye.
Cheers. Bye bye.